In the last lecture, we were looking at a balance equation for a spherical coordinate system. This is used in geometries which have spherical symmetry. For example, a particle, a spherical particle on which you specify a temperature at the surface and a different temperature far away, and you have to solve the heat conduction equation for the flux from the surface, for example. In that case, you would use a spherical coordinate system in which one of the coordinates is the distance from the center or the distance from the origin. And for a spherical particle, the distance from the origin is a constant on the surface of the particle. It is equal to the radius on the surface of the particle. There are two other coordinates, however, those turn out to be angles. For the present, we consider only spherically symmetric problems where the temperature or the concentration, for example, depends only upon the distance from the origin and not the orientation of the position vector. Okay. So, for a given distance from the origin, the temperature or concentration is the same regardless of the position of the orientation vector, okay, the orientation of the position vector. Okay. So, however you rotate the orientation the position vector around the origin, the temperature is the same. So, we wrote the mass balance equation for that case. Change in mass in differential volume is equal to mass in minus mass out plus the production. And in this case, the volume had two surfaces, inner surface area 4 pi r square, outer surface area 4 pi r plus delta r the whole square. Okay. So, these two surfaces have different areas. The volume is 4 pi r square delta r, the surface area times the thickness. And then we wrote the equation change in mass is equal to mass in minus mass out plus production, where change in mass is equal to the change in concentration times the volume 4 pi r square delta r. Mass in and mass out are the fluxes times the surface area times delta t, because the flux is a mass per unit area per unit time. Okay. That at r enters, that at r plus delta r leaves, and then you have production of mass. Based upon that, we had calculated this conservation equation. Okay. Based upon that, we had calculated this conservation equation, where it contains this 1 over r square d by dr of r square times gr. Okay. So, that is the difference from a spherical coordinate system which has 1 over r and a Cartesian coordinate system which has which does not contain any powers of the spatial coordinate. Okay. And these factors arise because the surface area is proportional to r in a cylindrical coordinate system, proportional to r square in a spherical coordinate system. Fick's law has the exact same form, okay, whether it's cylindrical, spherical and so on, and from that we get the conservation equations. We solved the equation at steady state in the absence of any sources or sinks, okay, and the temperature, the equation for the temperature we get is 1 over r square d by dr of r square dt by dr is equal to 0. This is valid, of course, for constant thermal diffusivity, okay, because we have taken the thermal diffusivity out of the derivative. Okay. This can be solved to get an expression for the temperature. Okay. So, the temperature expression is something like this. Okay. T minus T infinity by T naught minus T infinity is equal to capital R by small r. At r goes to infinity, the left side is 0 and the right side is also 0 because r is going to infinity, it is in the denominator. At r is equal to capital R, the left side is 1 and the right side is 1, and the temperature decays as 1 over r. I had also expressed it in terms of T star. Okay. Define a scaled temperature and a scaled radius. Okay. and you get a relation between T star is equal to 1 over R star. Okay. We had calculated the flux at R is equal to R, okay, minus K partial T by partial R, which is minus K into T naught minus T infinity by R into the derivative of T star with respect to R star. And we had got this expression for the flux. Average flux is the same as the local flux because this is a steady problem and there is no variation with respect to orientation on the surface, okay, of the sphere. Okay, the temperature is the same at any orientation on the surface. Okay. So, from that we had got the Nusselt number correlation. Nusselt number is equal to 2 because the length scale that you are using for the Nusselt number correlation is the diameter of the particle. Okay, we can also look at the heat transfer rate. Okay. QR is equal to minus K partial T by partial R. Okay. That was the solution that we had. Okay. We can write it in either dimensionless or dimensional form. Okay. It does not make very much difference. Okay. So, in this particular case, if you recall, I got, okay, is equal to minus K. Okay. So, let me write the expression for the temperature. Okay. T minus T naught is equal to, sorry, that was the dimensional form for the equation for the temperature. Okay. T minus T infinity by T naught minus T infinity is R by R. This will imply that T minus T infinity is equal to T naught minus T infinity into R by R. So, partial T by partial R is equal to minus T naught minus T infinity R by R square. If you substitute that here, you get QR is equal to K into T naught minus T infinity R by R square. Okay, so, that is the expression for the heat flux. The total heat transfer rate is the product of the heat flux and the surface area. Okay. Total heat transfer rate, energy transferred per unit time, okay, QR is equal to QR into 4 pi R square. Okay. Okay. That is the total heat transfer rate, total heat emitted by this sphere. I can alternatively express the temperature in terms of this heat, the total heat transfer rate, okay, by just substituting T naught minus T infinity is equal to QR by 4 pi K R. Okay. If I substitute that into this equation, okay, if I substitute that into this equation, okay, what I get is that T is equal to T infinity plus, okay, by 4 pi K R. Okay. So, the heat flux decreases as 1 over R square. Okay. Heat flux decreases as 1 over R square. The surface area increases proportional to 1 R square. The total heat transfer rate is independent of R, as you would expect, because the sphere is emitting, okay, the sphere is emitting heat, okay, the sphere is emitting heat energy, and there is no source or sink in the medium, and it is at steady state. Okay. What that implies is that the total heat energy coming out at any radius has to be the same as that coming out at any other radius at steady state. Okay. So, that is why the flux goes as 1 over r square, the heat transfer rate is a constant, temperature goes as 1 over r, okay, because if temperature goes as 1 over r, the flux is proportional to the derivative of that, which should go as 1 over r square. Also note that from this expression, okay, I can write that T minus T infinity is equal to q r by 4 pi k r. Okay. This expression is actually independent. Okay. This expression is independent of the radius of the sphere if the total heat generated is specified. Okay. This expression is independent of the radius of the sphere if the total heat generated is specified. Okay. So, therefore, regardless of the radius, if the total heat generated is specified, then the temperature from the temperature as a function of r depends only upon the total amount of heat generated per unit time. It does not depend upon the radius of the sphere. Expressed in terms of the temperature, of course, it depends upon the radius of the sphere. Okay, so. And then we had used this to calculate the correlation, okay, the Nusselt number correlation. I will just briefly compare this with the temperature field that we had for cylindrical coordinate. Okay. So, in this particular case, I said temperature on the sphere is fixed, temperature far away is fixed, T infinity far away, T naught at the surface, and then we calculated what was the temperature field, and then from that we calculated the heat flux, the average flux, and the Nusselt number correlation. Can you do that for a cylinder? Okay, if I have a cylinder of radius r, okay, why does nobody give us a Nusselt number correlation for this cylinder? Okay. The reason is because I have the equation for the temperature field is partial T by partial r is equal to 0. Okay. Which implies that r partial T by partial r is equal to a, partial T by partial r is equal to a by r, and T is equal to a ln r plus b. Okay, that was the temperature that we had derived for a cylinder. And if you try to impose T is equal to T infinity far away and T is equal to T naught at the surface, you can easily see that you cannot satisfy this boundary condition, because as r goes to infinity, the logarithm does not go to 0. Okay. Logarithm goes to infinity. Okay. So, because of that, you cannot satisfy this boundary condition. Steady heat conduction from a cylinder of infinite length does not have a solution into an infinite medium. Okay. We had solved earlier the temperature field for the cylinder for the temperature between two cylindrical surfaces. That had a solution. One cylinder in an infinite medium, that does not have a solution, because the solution for the temperature has a logarithm in it, and with that you cannot satisfy a constant temperature condition far away. So, the diffusion equation for a cylindrical coordinate system outside of a cylinder in an infinite medium does not have a solution, and therefore, in order to get the solution, one has to take into account the finite length of the cylinder in the third dimension perpendicular to the plane. Okay. So, so even though we may idealize it as a cylinder of infinite length in an infinite medium, that does not have a solution. You have to consider the conduction from a cylinder of finite length, and the extent to which conduction takes place is comparable to the length of the cylinder, okay, for this reason. Whereas for a sphere, conduction from a sphere into an infinite medium in 3 dimensions does have a solution. And that was the reason when we discussed conduction from a cylinder, we had actually taken 2 radii, okay, the inner and outer radius. Okay. So, the next example we can consider is conduction from spherical shell. Okay. So, this is a spherical shell of inner radius r I, outer radius r O, temperature T I on the inside, temperature T O on the outside. Steady state in the absence of sources or sinks of energy. Okay. So, how do we solve this problem? It is exactly similar to what we did for a cylinder. 1 by r square d by dr of r square partial t by partial r is equal to 0. I will do it in scaled coordinates. It is a little more convenient in scaled coordinates than to do it in unscaled coordinates. Okay. I will take r star is equal to r by ri, okay. T star is equal to t minus ti by to minus ti. Okay. With this, the boundary conditions become T star is equal to 0. Temperature is Ti, that means T star is equal to 0 at R star is equal to 1, at R is equal to capital R. Okay. T star is equal to 0 at R is equal to capital R. That means that T is equal to Ti on the inner surface at R is equal to Ri. And T star is equal to 1 at R star is equal to Ro by Ri. Okay. Outer cylinder radius is Ro, R star is equal to Ro by Ri and T star is equal to 1. And the equation becomes, okay, I can just scale it, okay. R star is linear in R and T star is linear in T, and therefore, if I scale the equation, I will get 1 over R star square d by d R star of R star square partial T star by partial R star is equal to 0. I will get R star square partial T by partial R star, integrating once, multiplying by R square and integrating one time. This will be a constant, I will call it as minus A. Okay. Okay. And T star is equal to minus A, this is plus A by R star plus B. Okay. And now I have to determine what are the constants A and B from the condition T star is equal to 0 at 1 and it is 1 at Ro by Ri. Okay. I can of course you can solve it, but the easy way to get the expression is to write this as, I know it has to be proportional to 1 over R. Okay. I know it has to be proportional to 1 over R. Therefore, I can just write it as 1 minus 1 by R star divided by 1 minus Ri by Ro. Okay. You can easily see that R star is equal to 1, this is equal to 0. So, it satisfies this boundary condition. Okay. At R star is equal to Ro by Ri, this is equal to 1. So, it satisfies this boundary condition. Okay. At R star is equal to 1, it is 0. So, the numerator is 0. R star is equal to Ro by Ri, the numerator is also equal to 1 over Ri by Ro, and so is the denominator. So, T star is equal to 1. Okay. Or to go back to scaled coordinates, I will get T minus Ti by To minus Ti is equal to 1 minus Ri by R by 1 minus Ri by Ro. Okay. So, there is the temperature field. Okay. I can get the heat flux, Qr is equal to minus K partial T by partial R. T star is TO minus TI into T star, temperatures TO minus TI into T star, okay. And on the denominator I have Ri partial T star by partial R star. Okay, so this is what you will get if you simplify this expression. Okay. Partial T star by partial R star is minus 1 over R star square. Okay, so let me just go through this in two steps. Into okay, I have to so this first term is just a constant. Okay, so that derivative is 0. The second term goes as minus 1 over R star. Okay, so I'll get plus 1 over R star square is the derivative in the numerator, and I get 1 over Rho in the denominator. Okay, and R star square, R star is R by Ri. Okay, so you get minus K into TO minus TI by Ri, Ri square by R square, okay, into 1 by 1 minus Rho by Ri. Okay. So, one factor of Ri will cancel here, and the second factor can be absorbed into the denominator. Okay. Second factor can be absorbed into the denominator, and finally I will get this as minus K into TO minus TI by R square 1 by Ri minus 1 by Rho. So, that is the heat flux. Heat transfer rate, okay, QR is equal to 4 pi R square QR. Surface area times the flux, okay, which is minus 4 pi K into TO minus TI by and the heat transfer resistance, okay, R is equal to minus delta T by QR, okay, which is minus TO minus TI by QR. Okay. This will be equal to 1 by Ri minus 1 by Ro divided by 4 pi K. Okay. So, this is the heat transfer resistance. Okay. This is the ratio of the temperature difference and the flux. Temperature difference equivalent to voltage difference, the rate of transport of heat equivalent to the current. The ratio of these two is the heat transfer resistance. Okay. And this is the expression 1 by Ri minus 1 by Ro divided by 4 pi K. Recall that for a Cartesian coordinate system, okay, this heat transfer resistance was equal to H by K A, okay, where h was the thickness of the plate and K A was the area. Okay. For a cylindrical, this was natural logarithm of ln of Rho by Ri by 2 pi K L, where L was the length of the cylinder along its axis perpendicular to the cross section of the cylinder. For a sphere, this is the heat transfer resistance. Okay. And if I have multiple spherical shells with different heat transfer resistances, the total resistance in this series configuration is just going to be equal to R1 plus R2 plus etc. Okay, where I will use this expression for the heat transfer resistance for conduction in multiple shells. Okay. So, with this I will complete our discussion of curvilinear coordinates. First, a cylindrical coordinate system, where I derived for you mass, momentum and energy conservations. Momentum conservation both in the axial and in the polar directions, okay, in the direction along the axis and in the direction around the axis, and we had solved some problems. For heat conduction at steady state, we had derived the heat transfer resistance. Similarly, for a spherical coordinate system, I had derived for you only the concentration and energy balance equations. It turns out that momentum balance is more complicated, okay, because momentum is a vector. You can have momentum along the radial direction, of course, but you can also have momentum around the axis in two different directions. And therefore, I derived for you only the heat conduction equation for the equation for mass diffusion and for heat conduction. And we had solved these, the mass diffusion and the heat conduction equation, in order to get the Nusselt number correlation for a spherical particle, which we had used earlier. This correlation which we had used earlier has been derived here. The procedure is what we will usually use to derive correlations. Solve for the fields, the temperature, the velocity or the concentration fields over the entire domain. From that solution, get the equation for the flux at the surface, average flux at the surface, and use the Nusselt number definition, scale the flux by the right side of Fick's law or Fourier's law to get what is the correlation for the Nusselt number as a function of the other dimensionless groups. In this particular case, at low Peclet number, fluid velocity is not important. Therefore, the Reynolds and the Peclet numbers are not important, and therefore, it is the Nusselt number is a constant, and that constant value is what we had derived over here. So, this completes our discussion of transport processes, Cartesian, cylindrical, spherical, only for the derivation of the equations, and then using the equations only for steady state solutions. In the next lecture, I will start discussion of pressure driven flows. Okay. All the flows that we were considering here contained only a shear stress. There was no pressure. That was because we were assuming that it was unidirectional, and therefore, the pressure variation was 0. Okay. In a pipe, for example, the flow is driven by a pressure difference across the two ends. Okay. So, that is a mechanism of transport that does not exist for mass and heat transfer. Momentum is a vector, and the velocity can be driven by a pressure difference which the analog of which is not present for mass and heat transfer. So, pressure driven flows is what we will consider in the next class. I will continue this then.